Alrighty, good afternoon, everyone, and welcome to the American Floral Endowment's Grow Pro webinar series. I'm your moderator, Michael Wijesinghe, and I'm an assistant grower for Bell Nursery in Springfield, Ohio. I help oversee and manage production of a wide variety of ornamentals for hundreds of stores across the country. Today's session is on reducing pesticides in surface and subsurface irrigation water. On behalf of the endowment, I'm excited to be part of AFE's Grow Pro webinar series that features a new topic every month presented by an industry expert. The webinars are free to everyone thanks to the generous support of AFE's sponsors. If you'd like to learn more about our sponsors, or if you are a supplier and interested in becoming a sponsor for a topic, you can find that information on AFE's website at endowment.org/growpro. Today's session was pre-recorded in English by Dr. Tom Fernandez. After the presentation, Dr. Fernandez will join us for a Q&A. Feel free to submit your questions through the Q&A feature or chat at any time. We'll answer as many as we can before the end of the hour, and unanswered questions may be answered through separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I'd like to share a bit about today's expert speaker, Dr. Tom Fernandez. Dr. Fernandez's research and extension program focus areas are on water quality and management for container nursery production. He is particularly interested in methods to conserve water and remediate agrochemicals from irrigation return flow and recycled production water. Along with water quality research, Tom is investigating the use of RFID to facilitate precision agriculture practices for container production. He works primarily with ornamental nursery industry, but has also worked with the fruit, vegetable, and Christmas tree industries related to water quality and irrigation management. Dr. Fernandez teaches landscape plant identification and nursery management at Michigan State University. Tom, welcome, and thank you for presenting today on reducing pesticides in surface water and subsurface irrigation water.
Okay, hello everyone. Thank you for inviting me to discuss some issues about pesticide movement in surface and subsurface irrigation return flow water. What we're going to do today is start out with some terminology, so we're all familiar with what I'm discussing, and there are some terms that are important as far as regulations. We'll talk about factors affecting pesticide transport, water and pesticide transport in a container production system. Then we'll go over a summary and then talk about some practices that you can use to reduce the transport of pesticides. Okay, so the water terms, the reason why this is important is because I did get involved in a situation where an operation was discussing their water movement and their pesticides with a new employee of a regulatory agency who misunderstood because they weren't using the proper terms, and that blew up into a fairly large problem. So let's make sure that we try to use the right terms when we're discussing water issues with agencies that have some regulatory power. Okay, so runoff, this is not a regulatory term. It's kind of a general term most people are familiar with. This is the surface movement of water. Infiltration, another non-regulatory term. This is water that enters the subsurface water system, basically becomes groundwater at some point. Operational water, this is water that has come into contact with the production surface. Now, I put this one in yellow highlight because in some states this is regulated. And the key point of this term is that it contacts your production surface, which may have some contaminants on it. Stormwater. Sometimes stormwater is lumped in with operational water. Sometimes it's separated out from operational water. In either case, some states regulate it. This is water from precipitation that does not pass over the production surface. All right, here's the one in red. That means it's even more important. This is one that's a federal regulation or a term in federal regulations. This is in the Clean Water Act. So this is water that was used for irrigation that returns to the hydrologic system or the outside environment. Non-point source pollution, another Clean Water Act term. And with regard to water, which we're most interested in our types of operation, non-point sources of pollution have no identifiable outlet. So it could be, for example, water moving across a field. You can't point to one source of that water flow. It's over an entire front. Point source pollution, on the other hand, comes from a specific outlet. Now that's a good thing for us, that for agriculture, we have an exception. All of agriculture's irrigation return flow is considered non-point source. And that's important because no permit is needed for non-point source pollution. Okay, even if it comes out of a point source, a pipe, a drainage ditch, a drain tile, for agriculture, it's considered non-point source pollution. Discharge water, we rarely have discharge water, or we have it in only a few parts of our operation. Think of tank, pesticide tank rinsate, anything you do in a pesticide mixing area, any water from that type of situation is potentially discharge water. So that's water being discharged from a point source. Don't use this term for irrigation. It could potentially get you in trouble. This requires a discharge permit, and NPDES is the specific type of permit through the Clean Water Act. Retention basins and retention reservoirs, either one, you could call them either one. This is something that has been constructed. It's artificial, and it's for retaining water that you might want to recycle or that you might want to capture and treat so that you can reduce the contaminant load. Don't use lakes or ponds or some other natural body term, water body term, to talk about a constructed reservoir or basin. This again can have regulatory ramifications. Okay, some important pesticides terms. These are not important as far as regulation. These are important as far as how water moves the pesticides. So we have solubility. This is the maximum amount of the compound, in this case pesticide, that will dissolve in water at a standard temperature. Adsorption coefficients. This is how strongly pesticides attach to a particular substance. And there are coefficients that have been determined for most pesticides, for soil, for organic matter, in some cases plastics. And you'll see them represented as KD for soil, KOC for organic matter, KP for plastic. So this is how tightly they bind to something. So high solubility usually means that a pesticide moves relatively quickly in large amounts. High adsorption means that it binds to something, so it's not as likely to move unless whatever it's bound to moves. So it still can move by erosion. Half-life is the amount of time it takes for half of the compound to degrade. We're not going to talk about that a lot, but it's kind of logical. The longer the half-life, the longer that compound will stay around. Volatility, the ability to convert to gas and be carried away into the atmosphere. Again, this is something that does happen, but it's not a major way for pesticides to move in our system. Concentration, this is important as far as its biological effects. So high concentrations, that's basically the dose, can have a high impact on biological systems. So think of LD50s. There are LC50s as well, lethal concentrations, the amount of compound it takes to kill half of a population. Daily load is the mass of the pesticide accumulated in one day from a contaminated water source. And this is related, in our case, to the impact of the contaminated source on the receiving water body. So it could be your retention basin, or it could be an external stream, whatever that water is moving into. Okay, let's talk about pesticide transport in container production. Okay, so this is what happens when we apply pesticides, or fertilizers for that matter. We can do it as liquids or granulars. A lot of times we apply them over the top of the crop during production or on the production surface. And it's nice to see this granular because it can show you where you've missed your target. So in the aisleway, we've got a lot of granules that didn't hit our containers. And then you can kind of see in here where it's missed, again, the target in these spaces between the pots. So the wider you spread out your plants, the more non-target spaces you're hitting with your pesticides. Then we turn on our irrigation water. And remember, water is what's driving pesticide movement in our production systems primarily. We start moving pesticides. And again, granular applications are typically easy to see. And you can see these yellow granules of snapshot moving in the irrigation water. Also, nutrients we typically top dress or might incorporate. They can leach through the bottom. Same thing with any pesticides we might use as a drench. They'll leach through and out of the container. And then all of that is going to end up moving into either our retention basins or potentially off-site if water is flowing off of our production operations. Okay, pesticide transport in our container production systems is primarily by water. You can see over here all of the different fates of pesticides. Some evaporate, some blows off and drift. This is typical of when we're applying the pesticide, not following pesticide application. We can have leaching down into the soil, into groundwater, and we can have runoff over the surface that can move into adjacent water systems. So shortly after we apply a pesticide, the liquid applied pesticides remain dissolved. If we irrigate or we get precipitation relatively quickly after applying a liquid, it can move very rapidly in water. Granulars will move suspended in water shortly after application. A day or more after application, the highly soluble pesticides, they've dried and formed a residue. They're likely to redissolve once you apply irrigation or if we have some precipitation. Now, I know greenhouses don't get a lot of precipitation, but greenhouses are producing more and more crops outdoors as well. Okay, high absorption pesticides will bind to particles. So they'll bind to soil, potting mix, leaf litter, plastics, but they can still move erosively as that soil particle or the peat particle moves around in your operation in the water. Low absorption pesticides, or where no binding surfaces are present, think of maybe a concrete floor, will continue to move with water. Granular pesticides will dissolve, and then they'll move like the other two examples. When they dissolve, think of them as initially shortly applied or shortly after application, and then after they've dissolved a day or more in the 1 day or greater application. So the greater the solubility, the more likely a pesticide is to move subsurface into the groundwater system. There are pesticides in nursery water and also in greenhouse water. These are some examples of pesticides, the concentration that was found and where they were found in these container production systems. Now, this is just nursery, but it applies to greenhouse movement as well. Here's pesticides in groundwater. Again, a whole string of pesticides that occur in groundwater and their concentrations. So we know it's moving to surface water and we know it's moving into the groundwater. So we want to reduce that as much as possible. Okay, I want to talk about a project that we did with SERI funding. We also got some funding from MSU and our Department of Agriculture. And what we wanted to do was look specifically at how pesticides move in a nursery container production system. So what we did is we built these raised beds. They were 2 feet high. The first foot was native soil. Then we put down a pond liner. On top of that, we put a layer of sand, covered it with the landscape fabric, typical of nursery production and some greenhouse production, graded it all to one point, so the water flowed in this pattern, put in some tanks so that we could collect water at the surface right off of the fabric, and then water right above that pond liner. So we were getting water movement through that 1 foot of sand. And then we put our plants and our treatments on top. Now, I'm going to show you 1 year of several years of experiments that we've run with this system. This one's interesting because it gives you a typical nursery overhead application rate. That's the control. It gives you a water saving overhead application rate. So what we did is we scheduled irrigation to replace 100% of the water that was used by the plant every day. And we use sensors to do that. That's a whole different topic, how you schedule irrigation with sensors. And then we did a spray stake treatment. And again, replacing 100% of the plant daily water use. So basically those are as close to zero leaching irrigation treatments as we can do. Now we can get away with that outdoors in Michigan, where we get rainfall greenhouses. You have to watch your leaching fraction a little bit more. Okay, we applied 9 pesticides over 3 application dates. We made them as tank mixes, and they were all applied as a sprayable liquid. So you can see all of the pesticides we used. Okay, we sampled the water. We collected water on days 1, 2, 4, 8, and 16 after application. We measured the volume of water we collected as well. So we get concentration, and we can calculate load now that we know the volume of water that we've collected. We also collected nutrients, but we're not going to be talking about that. They move similar to some pesticides. So you can think about it in the process of how pesticides move. All right, let's look at how the water moved, our irrigation dynamics. This is important because, again, pesticides are primarily being moved in water in our container production systems. So the amount of irrigation that we applied, and all of the graphs are going to look like this. The control are these green vertical stripes. The overhead based on plant water use is in orange, and the spray stake based on plant water use is the horizontal blue stripes. And you can see we've had a substantial reduction, around 50% reduction in the amount of water applied just by scheduling our overhead based on plant water use rather than a set amount. We reduced it by around 75% with the spray stake. So that's really great reductions in water movement. Okay, let's look at the return flow, the runoff basically that goes through over the surface and infiltrates downwards. So this is the total return flow. We have, of course, the most for the one that received most water, a nice reduction around 35% based on for overhead based on plant water use, and then a 60% reduction when we go to spray stakes. We can split that into surface and groundwater or infiltration movement. And again, that same pattern. It almost looks identical to the irrigation applied. One thing to notice is the difference in scales. We're 1/10 of the amount of runoff versus what we applied. The amount then infiltrated, not really much different. They're pretty much all the same. So let's see how pesticides moved in that. Again, we use these 9 pesticides. I'm only going to give you 3 as an example. One that's very highly mobile, acephate. We're going to also look at triflumazole, that's Terragard, a fungicide, it's slightly mobile, and then bifenthrin, Talstar. That's one that doesn't move very much at all. Okay, so for our highly mobile insecticide, acephate, here's how much we found in runoff. Again, the key is the same as far as colors. And over 16 days, you can see a lot of it comes off at the front and then it starts tailing off. By far the most coming from the overhead set amount, quite a bit less when we go to scheduling it based on plant water use, and almost nothing when we look at the spray stakes. Now, this is the runoff, so that makes sense. Overhead is hitting all of those non-target areas. Spray stake is only going into the pots. All right, how much moved downwards? What we see is a lag effect. So that makes sense. It takes a little while to move down through that foot of sand, and it takes another day before we start seeing pesticides moving into the groundwater or below the production surface. And that is a longer lag for the spray stakes. But again, the same pattern, most coming from the set amount overhead, less for overhead based on plant water use, and even less for spray stakes. Now let's look at the load, the actual total amount coming off per day. Pretty much the same pattern. Not quite as big a difference between the two overheads, but a huge difference with spray stakes for the runoff. And here's the total amount captured. And then the same lag that we're seeing with load. Now look at the difference in scale between these two though. So we're getting much, much more. The top of the line here is 10. The top is here, much more moving above ground in the surface runoff than moving below. Okay, so let's look at the total amount of acephate recovered. So this is the amount recovered versus what was applied. We're recovering almost 90% of the acephate from the two overhead treatments. That's a huge amount. The good news is we're only recovering around 5% with the spray stake treatments. Again, that's a lot, but much, much less than with the overhead systems. Again, we're hitting a lot of non-target areas with overhead irrigation, with both irrigation water and the pesticide that we applied. All right, let's look at triflumazole. So this is Terragard, a fungicide. It's a slightly mobile pesticide. First of all, notice the difference in the scale. So with acephate, our top scale was 3,000. So we're already doing quite a bit better by choosing a slightly mobile pesticide. Now we're at 30 as our top amount for parts per billion. Same kind of pattern. We have the most coming off in the overhead at a set amount. We have a little bit of a delay and less coming off with our overhead based on plant water use, and then the least for spray stakes. And again, that's surface runoff. Moving downwards, we have the same lag effect and pretty much the same pattern. The most for the overhead at a set amount, least for, or next for based on plant water use, and the least for spray stakes. The load, again, most for the overhead, and then almost nothing moving with the spray stakes. And then the infiltration load, again, look at the difference in scale. So we're at 0.06 and here we're at 0.004. And we were quite a bit more than both of these. I think we're in the tens for acephate. Again, a delay in movement as it goes downwards through that sand layer. A little bit of a catch up here between the two overhead treatments and substantially less for the spray stake. How much did we recover? This is a lot better news. So as we go from that very highly mobile pesticide, acephate, to a slightly mobile pesticide like triflumazole, we've gone from 90% to around 2% for our maximum. And the best news is for the spray stakes, almost nothing, 0.09% of what we applied is what we've recovered. Finally, for Talstar, a hardly mobile or barely mobile pesticide. Again, we have a change in scale. So acephate was 3,000, triflumazole was 30, and now we're at 1.5. So tremendously less movement when we change our pesticide properties. In this case, almost the same for both of the overhead treatments throughout the period, but almost nothing for the spray stakes. So that's in the runoff, surface runoff. This is moving downwards, almost nothing in any of them. So we've almost eliminated movement downwards through our system. The load, look at how small this scale is. So I think we're at 0.06 for triflumazole. Now we're at 0.004 for bifenthrin. So very, very little amount of bifenthrin moving in the runoff and also moving downward. This is even another 0.0001 moving downwards. So very little movement with this very sticky, low solubility pesticide. The amount of bifenthrin recovered, around 0.3, a little bit more than 0.1, and then just almost nothing, 0.003% recovered. Okay, so to summarize, if we compare to the 3/4 inch everyday irrigation, kind of as an industry nursery standard for 3-gallon pots, our irrigation volume, the driving force for pesticide movement, is reduced by 76% for spray stake, 47% by overhead when we schedule it based on plant use. We reduce our irrigation return flow by 60% with spray stakes and by 30% when we schedule our overhead using plant daily water use. Pesticide movement is related to water solubility and absorption. So high solubility, low absorption pesticides like acephate are going to have high transport in surface and subsurface water. As the solubility decreases, and more importantly, the adsorption coefficients increase, subsurface transport is reduced more than surface transport, but both of them were reduced quite a bit compared to our highly mobile pesticide. Pesticides move primarily by water, so whatever you can do to reduce your water use and your irrigation return flow, both surface runoff and infiltration into the groundwater, is going to reduce your agrochemical movement. We did have a few instances where we had high pesticide concentrations in our irrigation return flow, higher than our daily water use treatments, but still the load was much lower because we were not moving as much water. So to kind of take an overview of what happens when we apply pesticides, these are all of the processes that can occur. What happens when we reduce the amount of water used? So we can do that by spray stakes. We can do that by drip irrigation. We can do that by scheduling our irrigation based on plant water use. Or if we apply water on target, again, we can do that by spray stakes, drip irrigators, or we can use all of these things and use deficit or delayed irrigation. If we use a lower irrigation rate the first few days after applying a pesticide, or if we can even delay irrigation a day after applying a pesticide, we can reduce these processes, and that allows everything else, all these other things, actually degrade or stop movement of pesticides. The only thing we aren't changing is drift. So again, reduce the amount of water used, hit your target with your irrigation, and then use deficit or delayed irrigation. And you keep pesticides where you want them. You give them time for natural degradation processes to occur, and we decrease pesticide movement. So again, reducing pesticide movement, irrigate based on plant requirement, reduce off-target irrigation, delay irrigation as long as possible after pesticide application, Reduce your irrigation rate. Use a deficit irrigation following pesticide application for as many days as you can without reducing your crop growth and quality. Choose pesticides with low water solubility and high adsorption coefficients whenever possible. Now that's really advanced pesticide selection. I'll show you a website where you can do that, but that's more of a challenge. Recycle your irrigation runoff. If you capture your water and reuse it, the water is not leaving your operation. And so it should not be a problem for the surrounding ecosystems, and it's not going to be facing regulation. Okay, so the website that I use to find pesticide properties is right here. It's fairly easy to find. You can search whatever pesticide either by its trade name or pesticide chemical name and find out its solubility and its adsorption properties. Another really good site, so this is that SCRI project that funded the research that I showed you. It has lots of other information on water, scheduling irrigation, sanitizing irrigation water. How do you set up retention basins? So lots of information on water. So that's a good one to check out for this and other types of information. Of course, this is a lot of work over many, many years. I just showed you 1 year. It took a lot of people to do it. We have a team at Michigan State that was working on it. Some have moved on to other organizations. Folks down at the University of Florida were involved in helping with pesticide analysis. And we didn't talk about nutrient movement, but we had collaborators at Virginia Tech looking at nutrient movement as well. And of course, funding from a few grant agencies and then use of materials from some industry members. So certainly want to thank everybody involved in making sure this research was able to be conducted. So with that, if there are any questions, I'd be happy to take them.
Awesome. Thank you, Tom. It appears I got some questions here in our chat and our Q&A box. You guys are more than welcome to keep them coming as we start answering some of them. The first one I have is from David. Dr. Fernandez, do you have a presentation or paper available regarding the irrigation practices and timing for the study that you mentioned?
Yeah, definitely. I have some presentations that I've made. I don't think any have been recorded, but there are some that I have on a PowerPoint. And then papers, as far as, what are you asking as far as the actual studies or the methods that we use, like the irrigation scheduling and those types of things? We have published in scientific journals so far, but we haven't published a lot of that in trade journals yet. But we are working on that.
Awesome. I have another one from Sarah asking, why were these particular pesticides chosen? Is it because of their common use in Michigan crops or because they represent different IRAC groups?
We chose this. So this was, as I mentioned, part of an SCRI grant, and it was a national team. So we had people from all over the country, Florida, California, Texas, everywhere. What we wanted to do with our pesticide selection was choose a range of pesticide properties. The pesticides weren't as important to us as the properties were. So we wanted a range of highly soluble, low adsorption to high adsorption and low solubility. And so if you remember that one slide, all those 9 pesticides, we had that whole range of mobility. Again, that relates to solubility and adsorption. And then we did a couple of the pesticides were requested by growers. I didn't show glyphosate. We did a study including glyphosate 1 year, of course, a very popular and a very weird pesticide as far as the way it moves. Some of acephate is so commonly used. another one, bifenthrin Talstar, was requested by several growers on our advisory committee. So that's how we selected them. But the primary reason for selecting them was to give us a range of properties. So what we hope to be able to do with that is say, if you have a pesticide with a very high solubility factor and a low adsorption factor, this is how it's likely to move.
Fantastic. So another one I have, I know you answered it partially with the PubChem link, but I was wondering, or one of the viewers was wondering if there was any other resources you could recommend for finding about pesticide mobility or absorption.
Yeah, the PubChem is a really good one. It's pretty technical, and you might have to scroll through a bit to find what you want. You can also just do easy Google searches, and I do that a lot of times. If I don't have the time to dig through the PubChem, I'll just say solubility of acephate, and it usually takes you quickly to something. There's another one, eToxNet, all one word. If you just search in eToxNet, it should take you to that site. And again, that's another searchable database. And maybe I should have given that link because it's a little easier sometimes. And it will give you the same properties. It'll give you solubility and adsorption and a lot of other information. So, I mean, these are great sites from the point of view of a scientist. They have a lot of information on it that you might not be that interested in.
All right. So besides pesticides, what about like things like plant growth regulators, nutrients? Do they move similar to pesticides throughout the water?
Yeah, absolutely. So that's a really good question. I know a lot of greenhouse operations use quite a bit of growth regulators. You might use some antibiotics, certainly nutrients. Everyone uses fertilizers. And again, it's going to depend on the actual compound and how it moves. In general, the same principle applies though. Depending on solubility and adsorption coefficient, that's going to give you an indication of how much it moves. The higher the solubility, the more likely it is to move. The lower the adsorption coefficient, the more it's likely to move. So you can kind of use those two characteristics to judge, or at least if you look through those websites, those databases, you can. There are so many chemicals used. It would be really nice if the manufacturers added that one more bit of information to their labels, but there might be reasons that that's not done.
Yeah, keep on selling their stuff.
Well, there's some things that need to be soluble. You think of some of the drenches, right? They need to go into the substrate, and then the plant needs to take them up. If they bind really strongly, the plant won't be able to take them up. So there are reasons for some of these chemical characteristics.
Awesome. So your presentation was mainly about nurseries. How could you bring stuff from your presentation into the greenhouse world?
Yeah, I think probably the main difference is that you guys have lids right on top of your production. Nursery production, kind of the same production systems. If I've been to a lot of greenhouses, actually I grew up in a greenhouse industry. My grandparents had a greenhouse. They just grew on the natural floor, the dirt, the soil, right? So they had no ground cover down. This was in Florida, so there was a lot of sand, and the water would just run right through any excess water. So I've started with that. I've seen, of course, lots of flood floors, lots of solid concrete floors, seen fabric floors, seen gravel, rock, pea gravel, all kinds of different floors. And water is going to move downward in greenhouse operations. So there is the potential for water to move down into groundwater. I think probably the volumes of water that you're using, depending on how wisely it's used, and that depends on the operation, depends on how much you're going to push water down. You've cut out rainfall, so at least you're not pushing, you don't have that additional push of rain. Certainly water is going to move outside of greenhouses by some mechanism. Even if you're using flood and you have flood tanks, those tanks have to be purged every once in a while. And so that water is going to leave your operation. So these same ideas about pesticide movement apply to greenhouse operations, except you just take the precipitation out.
Awesome. So you briefly touched on flood tanks right there. What would you say happens with pesticides and other chemicals that are being recycled in those flood tanks?
So that's a really good question. And that goes back to growth regulators. And I know a lot of growers, if they're using growth regulators, have found some of their plants not growing as well as they should if they're using flood floors. And so most growers that do that type of irrigation will separate out plants by sensitivity if they're using growth regulators, right? So you might not flood irrigate those. You might use a fresh source of water to irrigate plants that are sensitive to growth regulators. And then I've got quite a few greenhouses now that have expanded into what we think of as nursery production as well, where they're producing outside without a roof. And, growing something like mums, a real common crop to grow outdoors now. And also pretty tolerant of a lot of the growth regulators. So using a crop that's tolerant to use irrigation that's been contaminated with something like that, a chemical with a pretty long, this is where half-life comes in, right? How persistent that chemical is. And so some of the growth regulators are a little more persistent. So you can use that irrigation on tolerant plants. But it's true, we do have to be aware and careful with the chemicals that we're using whenever we recycle water. A lot of times we think of herbicides as being the chemicals that damage plants, but there are some pesticides, some insecticides, and some fungicides that will damage particular plants as well. And we need to be aware of how those are being recycled in ebb and flow systems, or if we're using recycled reservoirs.
Yeah, that's a great point. I've seen exactly what you're talking about with paclobutrazol and some flood floors.
Exactly.
So we're gonna go through and do a couple more questions, one or two more. If there's any other questions out there, feel free to send them in so we can get them asked. One I have here is, if I delay irrigation and decrease irrigation following pesticide application, what happens to plant growth?
Right, and so that's why I always follow that up with if possible. And there's a lot to talk about there, right? So I know Mark Van Aerosol, I think a lot of people are familiar with Mark's work. Earlier on when he was doing some work with water, he was using water to act as a growth regulator. So you can use water to kind of control the expansion of your crop. So it could be beneficial. Of course, if you dry your plants out too much, you may never be able to re-wet them. So you have to be careful of when you try deficit or delayed irrigations. And that's something for advanced growers. If you do it early in the crop cycle, where the plants aren't needing water every day, they're a little more tolerant of a delay in irrigation. Or if you've just potted up, something like that, where you have a bigger reservoir that the plant hasn't taken advantage of yet. In those cases, it's a lot easier, a lot safer to delay irrigation. As you get closer to harvest, when you're ready to ship, the plants are full, then you need to be really cautious by using those types of approaches, because you can dry your plants out very quickly and ruin your crop. So always remember, you have to be aware of what stage your plant is in and whether they can tolerate that type of mild stress. In nursery production, we've done for over 10 years deficit irrigations and with woody plants, and they are much more tolerant. So they can take longer. Actually, they're more tolerant than I ever thought. So they can take quite a bit of deficit irrigation. We've gone 3 or 4 days of going negative leaching fraction, if that's a term, right? We've given them 75% of what they used in a day for 3 days in a row. And that's pretty tolerant for large, mature nursery woody plants. It's going to be different with herbaceous plants. So just aware of where your crop is in its cycle and whether it can tolerate that type of treatment.
Awesome. Well, that was great advice. I don't think we have any other questions here, so we're going to go ahead and wrap up. So thank you very much, Tom.
You bet.
And-
One more comment, if I can make it catch you right before we leave.
Yeah.
Someone asked about publications. I assume from the host, I can get you information to post somewhere. Is that right?
Yes, we can make the publications, any links that you want to make available with the recording on our website, which is GrowPro, endowment.org/GrowPro. I'll put it in the chat.
Okay, perfect.
Awesome. Alrighty, so I'd like to thank everyone for joining us today for another session of AFE's GrowPro webinar series. Love if everyone could join us next month for Dr. Royal Hines' session on diff and graphical tracking on Tuesday, August 23rd at 1 p.m. You can register at endowment.org/GrowPro. While you're there, check out past webinar recordings, other grower-related resources, and research reports, and information from Dr. Tom's presentation today, all available free thanks to industry support. We ask that you please complete the brief survey about today's session, where you can suggest additional topics and help us continue to improve these webinars in the future. Thank you again for joining us, and have a great day.
All right. Thank you, everyone.